All right, so let's take a look at our lesson for today. So I know, we've been enjoying the definition of the derivative, and you probably wish that we would never leave the definition of the derivative, but I just have to tell you today we're going to learn some rules that will take the place of some of the things that we do with the definition of the derivative. I know, it's inevitable. So if we do the derivative of a constant, so we're starting rules, and there are actually a lot of rules for derivatives. There's a lot of them, and they will make our lives easier. It's an easier computation than the definition of the derivative, but there's still rules that we have to know how to use. So the first one we talk about is the derivative of a constant is 0. So for example, if I did the derivative of 5, I would get 0. That's what it means. The derivative of the constant is 0. More unusual, which they like to try to trick us, the derivative of, say, pi squared, is 0. I know it looks weird, but pi squared is just a number, right? It's whatever, 3.14 squared. It's just a number. It's still 0. So that's how it could trick us with the derivative of a constant. The second rule that we're going to look at it's called the constant multiple rule. And basically what that means is that if we do have a constant that's being multiplied to a function, what I'm allowed to do is pull it in the front, take the derivative of the function, and then apply it or multiply by it. That's all. It just allows us to do work. I don't know, sometimes it makes our job easier. The power rule, this is the big one that we're learning today. So we're going to make some notes on here. So it's important to note that the power rule works, I'm just going to say only works on polynomials. The power rule is one of the easiest of the derivative rules. And when I teach it to you, it's easy, and so students want to use it for everything, but it doesn't work on everything. It only works on polynomials. So for example, if I want to do the derivative of, say, let's just do some x cubed, derivative of x cubed. So what this formula says is I take the exponent and I bring it down in front of the variable. I copy the variable down, and then I subtract 1 from the exponent. So the derivative would actually be, 3 minus 1. Then the derivative would actually be 3x squared. That's the power rule. Now, additionally, let's say I'm taking the derivative of, 2x cubed. Let's see how that applies. So when I take the derivative, I bring the 3 down. I have a 2 there that's already there that I have to multiply by, and then I subtract 1. So my answer would be 6x squared. So this number in front serves as a multiplier. It's this business right here, this C business. Notice how I didn't really do anything to it. I just left it there. And then I took the derivative of x cubed, and then I applied it. I multiplied by it. Okay, so that's a couple of examples on power rule. Are there any questions on power rule? Okay. 2 other rules. This 2 that I have underlined, that was in the problem. We're supposed to take the derivative of 2x cubed. That was what our task was. And so the 2, I just left there. It's just hanging out, not doing anything to it, much like this C. It's just there as a multiplier. Okay? And so perhaps it would be easier to see if I left a 2 right here, and then I've got that 3 there, right? This 2 is this 2. They're not doing anything, it's just hanging out. This 3 came down, and that's where that 3 comes from. Okay? All right. So now, as we're looking at our last rules, it is possible to take the derivative. If we're adding two functions together, it is possible and okay to take the derivative of the first and then add to it the derivative of the second. That's an okay thing to do. The same with subtracting. If we're taking the derivative of two functions that are being subtracted, it is perfectly okay to take the derivative of the first one and then subtract the derivative of the second one. That's an okay thing to do. Now, as we're talking about that, I need to make sure we understand that it is not okay if we're multiplying or dividing to do this kind of thing. That is not okay. So it's not okay to, if we're doing the derivative of f of x times g of x, not okay to split these. This requires a different rule. It's called the product rule, which we'll learn in a bit.
So you can only do that with subtraction.
You can only do this splitting thing with adding and subtracting. Cannot do it with multiplying and dividing. Okay? It's not okay. It's not okay to split for the dividing either. That is not okay. Really important. It's not okay. That is not okay to split those up. Okay? It only works with adding and subtracting. So that's really important to us. And we'll learn more about it later. But I just need to, as we're talking about these kind of rules, I need you to know that those aren't okay. Okay? All right, let's work some examples. So before, if we were going to find the derivative, we would use our definition of the derivative. Now we're going to practice, in this case, we're going to practice the power rule. So the first thing that I'm going to do, I can't, so we cannot take derivatives in this form. And what I mean by the form is radicals. We can't do a derivative of a function in radical form. We have to change it to exponents. So that's the first thing I'm going to do. I'm just going to rewrite this. So this is 6x to the 1/2. Remember, square root of x can be written as x to the 1/2 minus 4x cubed plus 9. Okay, so that's what I'm taking the derivative of. I'm just really, it would be better to rewrite it before we get into this. So the first thing I'm going to do is I'm going to find g prime of x. Please don't try to put the number 4 in before you take the derivative. That will not lead to a good place. Take the derivative first and then put the 4 in. So now what we're going to do is we're going to focus on this number right here, this term. I'm going to take the derivative of it. So I've got that 6 that's hanging out. I bring the 1/2 down, x. 1/2 minus 1 is a negative 1/2. Minus. That's, I took the derivative of the first thing. Now we're going to go to the second term. So I have the 4 there. It's just hanging out. I'm bringing the 3 down. And then I'm doing 3 minus 1 is 2. And the derivative of 9 is 0, right? The derivative of the constant is 0. So let's clean this up a little bit so it's easier to work with. So g prime is going to be 3 over square root of x. Again, I'm just rewriting it so when I plug a 4 in, my life is easier. Minus 12x squared. Okay, great. Now we want to find g prime of 4.
Just get rid of the 9.
The derivative of a constant is 0. So yes, it went to 0. It's gone. It's sad, but it's gone. Okay. Okay, so now I'm going to plug in the 4. 3 over the square root of 4 minus 12 times 4 squared. And that is 3 halves. And 12 times 16 is 192. So g prime of 4 is negative 190.5, or negative 190 and 1/2.
There's a 9 at the end of that problem. Do we add that or no?
Okay, so let's go back to our rule up here. So if I take the derivative of a constant, I get 0. Okay, and 9 is the constant. So I took the derivative of 9 and it's gone. It's just gone. Is that okay? Okay. All right, questions on number 1. Yes.
Why did you put like the 3 over that?
Okay, so what I'm doing is I'm taking this and I'm making it more doable for me, because that's really hard. I mean, what is root x to the negative 1/2 power? I mean, I don't even know what that is, right?
I didn't realize it was the negative.
It's negative, yeah. So it has to go to the bottom. That's a algebra thingy. Okay, any other questions on this? All right. So what this one is, now, what we want to do here is step back. On a problem like this h goes to 0 with the h on the bottom. That should look familiar to you. It should remind you of something that you've memorized, right? Definition of the derivative. This is what this should remind you of. And so this is a problem that we need to recognize. We need to recognize this as definition of the derivative. Because trying to work that limit like it is right now would be exceedingly difficult. I don't know about you, but I don't want to multiply 1 plus h out 8 times. And I don't want to multiply 1 plus h out 3 times. I really don't want to do that. Okay, so we recognize this as the definition of the derivative. So I'm going to write the definition of the derivative. I'm going to put it right underneath it. So the limit as h goes to 0 of f of x plus h minus f of x over h. Okay. So as we compare these two, I hope that you're noticing that this, which is an x, has been taken the place with constants. So in this form, this would give us f prime of x. In this form, the one that they're doing, f of 1 plus h minus f of 1 over h, this is going to give us f prime of 1. Just replacing the x with a 1 is basically doing that. We're replacing this x with a 1. And that's what the formula is doing. I'm sorry?
Why is there another h in the limit? It's just 1. Like, why are you not moving this?
Are you talking about this right here?
Yeah.
Okay, because this whole thing is f of x plus h. And I'll get into the pieces of it in just a second. This piece is f of x plus h, and actually it's 1 plus h, and this is f of x. This little piece right here, the minus part. Okay? All right. So what is this doing? So why are we doing this? The reason we're doing this is because this is the kind of way that we are faced with knowing the definition of the derivative on problems. I mean, this is usually how, geez Louise. Okay, that's a 1 plus h, and that's a 1. Okay. This is important that we recognize this because we're going to be faced with problems exactly like this. So how do we do this without doing the limit? What is this saying? This is saying that if I can figure out what f is, if I can figure that out and I can take the derivative of it and stick a 1 in it, I'm going to have my answer without doing the limit at all. That's what I'm looking for. So as I look at my function, this f of 1 plus h business, and that's the f of 1. So f is actually x to the 8th plus x cubed. Now I'm going to pause there for a second. How do I know that f of x, how do I know what the function is? Well, I look up there at the limit, and I see this part that I have, this part right here that we're talking about. That part has the 1 plus h in it. That's the part that's f of 1 plus h. What happens if I take this and I stick a 1 plus h in it, and I take this and I stick a 1 plus h in it? I get exactly that. Okay, are we together?
So the function of like 1 plus h equal like 1 plus h to the 8th.
So what I'm doing is I'm utilizing this definition. I'm pulling out f of 1 plus h. I'm trying to figure out what is f of x. That's what I'm trying to figure out. What is it? So I have to look up in the formula, and I look to see which things have the 1 plus h in them. That's going to be the f. F has had 1 plus h stuck where the x is. Okay, this is where the x is. This is where the x is. That's x to the 8th plus x to the 3rd. Okay, so now, well, that's not bad. I can take the derivative of that, right? What's the derivative of x to the 8th? Using a power rule. 8x to the 7th. What's the derivative of x cubed? Using the power rule. 3x squared. What happens when I put a 1 in there? 8 times 1 to the 7th plus 3 times 1 to the 2nd. I get 11. So f prime of 1 is 11. Now, if we went and worked out that crazy limit and took the really long time that it would take us to do that crazy limit, we would get the answer of 11 in the end, after a long time. So that's the benefit of recognizing that this is the definition of the derivative. So that's really our first step. Our first step is to recognize that this is the definition of the derivative. Once we've recognized it, then we should write down the definition of the derivative and try to figure out what have they done to it. What have they done to it? What are they asking for? So I want to pause here for a second. Questions on that? And we will see this kind of problem over and over again. So although we're not using definition of the derivative to actually find derivatives anymore, we're still going to use it all the time. All right, are we okay? Okay. Number 3. So here they're asking us to find g prime of 5. And they're actually giving us, and so we're going to do that in just a moment, but this problem is referring to this graph. We're going to have to pull values off of this graph. So before I get into the values, I want to just do the abstract. let's just find g prime. Let's just find g prime of x. 3 is a multiplier, so it's just hanging out there. The derivative of f is f prime, and I'm just going to put the x in there so it's prettier, I guess, minus g is just a function. The derivative of g is g prime. That's my g prime of x. Okay, now let's find g prime. Let's write out the word or the equation for g prime of 5. G prime of 5 is going to be 3 times f prime of 5 minus g prime of 5. I want to pause there for just a moment. So are we all okay? I found g prime, and then I plugged a 5 in. Okay, now my job is going to be to get these values from the graph. That's where I'm going to find them. Okay, so let's look to see where g prime of 5 would be. Now, so f prime of 5. Sorry, we need both g prime and f prime. Let's work on the first one first. So f is the black lines. So f prime of 5, here's 5. So I need this slope, right? We read the derivative is the slope. So I'm looking for this slope. I'm looking for the slope exactly actually at this point right here. It looks like that slope is 1. That slope is 1. So I'm going to replace, so we've got 3 times 1. Okay, now let's find g prime of 5. That's the red one. So we're looking at this slope right here. Okay, it's the red one. So what is that? That looks to me like that slope is -1. Okay, so I'm going to replace g prime of 5 with -1.
How do we know like which side, like which slope to use, like the one on the left or the one on the right for the graph?
So the f is the black one and g is the red one. Okay, and we're looking at the slope at 5. So we're looking at this at 5. It's at 5. Both of these are at 5. Is what we're looking at. Does that make sense? Okay. Okay. So then my answer is going to be 3 plus 1 or 4. Okay. How are we doing? We doing okay? Okay. So we're working through problems, different kinds of problems, experimenting or understanding how the product rule works in different circumstances. So we have looked at the very first problem that we did. We looked to see how the power rule works in just a standard situation. The second one, we looked to see how we could utilize the power rule when we're faced with the definition of the derivative. The third one, we're looking how we can use the power rule when, or just a derivative rule when we have a graph to get values off of. Okay, so we're doing a variety of different ways of using it so you can see how it's used. Are we okay? All right, number 4. So in this particular case, we've got some values. I mean, right now I don't know what we're using them for. I'm going to highlight them. We'll come back to them. I'm sure we'll need them. Maybe we will need them both. Maybe we won't. Who knows? But that's what they have for us. They tell us h is this weird function. They want us to find h prime of 0. Okay, so first up, I need to find h prime of x. So 3 is just a constant. It's just hanging out. The derivative of f is f prime minus 2. 2 is just hanging out. The derivative of g is g prime. The negative 5 is just hanging out. Now, the derivative of cosine, we will learn in the next class period, so you don't have to know this. Just write it down. We haven't learned it yet, but it happens to pop up in this problem. We learn derivatives of cosine and sine in the next lesson. So the derivative of cosine is negative sine. And again, you don't need to know that. Just write it down. And what is the derivative of negative 3? 0. It's gone. All right. So now I need to know h prime of 0. So I'm going to plug a 0 in. So that means 3 times f prime of 0 minus 2 times g prime of 0 plus 5 times sine of 0. And that's a unit circle value that we should know, right? Sine of 0. What is sine of 0? 0. That's a unit circle value we should know. This is going to turn to a 0. All right, so let's see if they gave us the information we need. I hope so. So f prime of 0, do they have that? Yeah, it's right up here. F prime of 0 is 3 minus 2 times g prime of 0. Did they give that to us? Yep, they did. They have it right here. G prime of 0 is 7. And then we just said using unit circle values, sine of 0 is 0. And so completing our arithmetic at this point, we've got, what, 9 minus, is that 14? So what is that? It's negative 5. Oh my gosh. Thank you, Siri. I didn't even ask you. That was my watch. Can you believe that? Oh my goodness gracious. Sorry. H prime of 0 is negative 5. You know, she hasn't done that like ever. I don't know why she did that. I don't know. Usually I get in trouble in BC. I teach sequences in series, and I'm talking about series, and she just pops up. What? Yes, can I help you? I'm like, no, I'm not talking about series. But I've never had her do arithmetic for me. Okay, that's fine. We're good. We have one more problem to do, and this is a free response. You have one just like it, although different, in AP Classroom. Just like this, but of course different numbers and stuff. So let's focus on this for a bit, do our free response. Okay, so we have an excavation site. The amount of dirt that's been removed in cubic meters is modeled by that function f. And okay, great. So g is a differentiable function. So let's underline these things. So what they're telling us might not be important right now, but it probably is going to have some importance later. So we should probably pay attention and like underline or do something. So here's our units are cubic meters. So G is differentiable. That's probably going to be important to us. T is measured in hours, and we've got cubic meters. Okay, so those are kind of clues right there. So let's study what we have for a moment. We have a piecewise function, and from 0 to 6, it's this polynomial. Oh, and by the way, yes, I typed all this up, and yes, I made a typo. I'm sorry. This should be a 3. If you would change that for me, that squared should be cubed. I made a little mistake. Okay, so that's t cubed over 12. And then from 6 to 12, we have this weird table thing going on. Okay, well, we need to make note of what's going on. So according to the model F, what is the average rate of change? This word should make a formula come out in your brain. Those words should make you think of a formula. Average rate of change. Okay, that's a formula you've memorized. You should probably write it down. F of B minus F of A over B minus A. That's the formula they're wanting us to use. of the amount of dirt removed over the time period 6 to 12. So if we're in 6 to 12, we need to use this branch, right? The bottom branch of my piecewise function. So that means we've got to use this little table going on over here. So we need the average rate of change from 6 to 12. Okay, so that would be, and I'm going to use of f. So let me fix this. So put the actual numbers in. So this would be f of 12 minus f of 6 over 12 minus 6. And since we're between 6 and 12, this is going to be the same thing as g of 12 minus g of 6 over 12 minus 6. And you might think, my goodness, why is she doing that? That's like duh. Okay, you really need to. What we're doing is we're establishing the reason we can use g to approximate f. How are we able to do that? Well, we're able to do that because g is part of the function f, only the part between 6 and 12. So yes, you need to write that down. And this is going to be the same as, so g of 12 is 474 minus g of 6 is 306 over 12 minus 6. And that is 108 over 6, which is 28. And let's put units with it. I know they didn't ask, but we need to do it anyway. It's cubic meters.
It's 168.
What is it?
It's 168, not 100.
I must have had the, okay. Yeah, I just wrote it down wrong. 28 cubic meters per hour. So 168 divided by 6 is 28, isn't it?
Mm-hmm.
Yeah. Another typo. My goodness gracious, I must have been like, I don't know what's going on. All right, so are we okay? Part B, use the data in the table to approximate f prime of 9, the instantaneous rate of change in the amount of dirt removed in cubic meters per hour at time t equals 9. Show computations that lead to your answer. Okay, well, we've done this before, right? We know how to approximate the derivative given function values. Right, what do? So we go to where 9 would be. 9 is right in here, right? 9's right in there. And we do our average rate of change. We're using instantaneous, to approximate the instantaneous rate of change, we're using average rate of change. We recall we've done that before, right? We did that in the last class period. Okay, so we've got, let's see, we've got, so f prime of 9 is going to be approximately 428 minus 376 over 10 minus 8, which should be, unless I made another typo, 52 over 2, which is 26 cubic meters per hour. Okay, how are we doing? Okay, continuity, continuous on 0 to 12. Okay, that's like the hardest one right there. It's going to take a lot. I want to go to D and then I'm going to come back to C. Okay, which is something, you know, on your test or whatever, it's certainly fine for you to do, skip around. So D wants us to find f prime of 2, the instantaneous rate of change of the amount of dirt removed in cubic meters per hour. So f prime of 2, let's look back at our piecewise function. F prime of 2, we would get from this top piece, right? That top piece is what would give us, because that's from 0 to 6. So that's where the 2 would be. So we need to find f prime of t. So we're going to use the power rule. So the derivative of 48t is 48. The derivative of t squared is 2t. and the derivative of negative t cubed over 12. So I'm just going to pull out the negative 1/12. That's just a constant. If we could write this as negative 112t cubed. That's okay to do. So I'm just showing you it's okay to write that as negative 112t cubed. That's an okay thing to do. And it makes our life easier when we're doing power rule, right? Because we bring the 3 down front, and 3/12 is 1/4, right? 3/12, where are we? 3/12. So we bring the 3 down. We get just a 3. I'm just going to leave the 12 there. Then t squared. What's that? This is just times 3 times t squared. All right, and this works for 0 to 6. That's where that works for. Well, all the way up to 6, not including 6. So to find f prime of 2, we would just do 48 plus 2 times 2 minus 1/4 times 2 squared, and that would give us 51 cubic meters per hour. Okay, so that's just power rule. Now let's go back to continuity. Let's talk about why this is a little bit harder. This is hard. Well, first of all, let me pause. Are we okay on part D? Yes? Okay, so let's look at part C. Part C is a little bit more challenging because I've got a piecewise function, right? This is weird. So I've got to do really 3 things. So let's just, I'm going to make little notes up here. We need to do 3 things. So number 1, and then it does that. Don't y'all hate it when it does that? Does that ever do that to y'all, or just me? Oh my gosh.
Yeah, I think it's supposed to be like 4 times.
Oh my gosh, that drives me so crazy. Okay, we need to do 3 things. Number 1, we need to make sure f is continuous from 0 to 6. We need to do that. We need to check that out. Number 2, we need to make sure f is continuous from 6 to 12. Number 3, we need to make sure f is continuous at the split, which is at 6. So we have 3 things to do. So that's why I said this is harder. We'll save this to last. So I need to make sure f is continuous on the first branch. I need to make sure f is continuous on the second branch. And I need to make sure that it's continuous when the branches meet. So that's a lot. Okay, but we can do this. So let's look at the first branch. The first branch of our piecewise function is a polynomial. Well, polynomials are continuous all the time, right? We can know by inspection. So let's write that out. So f is a polynomial from 0 to t to 6. Therefore, f is continuous from 0 to t to 6, because polynomials are always continuous. Great, that was easy. That's step 1. Make sure f is continuous on the top branch. Step 2, make sure f is continuous on the bottom branch. Well, the bottom is g, which is that weird table business. and look really buried over here. Buried over here, it says G is differentiable. That's important to our continuity business over here. So let's walk through that. Because G is differentiable, G is continuous. So differentiability implies continuity. To be differentiable, you have to be continuous. You don't have a choice. Because G is differentiable, G is continuous, and f of t equals G of t for 6 to 12. Okay, step 2 is done. So great. The second part of my piecewise is differentiable, and so therefore continuous. Wonderful. The last part is to see if they are continuous, if they join correctly. Okay, that means we have to do one-sided limits. Y'all are like, this just keeps going on and on. When is this going to be over? Soon. Soon. Okay, so we've got to do the limit as t goes to 6. Let's go from the left. And that's of our function 48t plus t squared minus t cubed over 12. So what do? We plug in 6 plus 6 squared. And this, I'm just saying, this is a lot of numbers for me. I would not make you do this without a calculator. That's just too much. This is 306. So from the left side is 306. Do we all understand why I'm saying that's from the left? Right? Because that's the piece that's on the left of 6. If you look up here, here's 6. On the left of 6 is this piece. That's on the left of 6. On the right of 6 is the table. Okay, so if we're going to 6, from the right, we're going to hit 306. Okay, so here we go. The limit as t goes to 6 from the right of f of t would be the same as f of 6, which is the same as g of 6. See, we got to put that g and f, relationship in, which is 306. Okay, well, great. So since the limit as t goes to 6 from the left of f is the same as the limit as t goes to 6 from the right, f is continuous at 6. That's definition of continuity, or part of it. Whew. Okay, we did step 1, step 2, step 3. Therefore, f is continuous from 0 to 12. Whew.